So, we want to continue with our pressure investigation. I won't see you today, 8A, so I thought I would make this little video that you could look at on Wednesday. Why does air move in the atmosphere? Well, you may remember the Earth is unevenly heated. Half of the Earth is getting energy from the sun, and half is losing energy as heat is released, infrared radiation is released from the Earth at night. Uneven heating causes air to rise and sink in the troposphere, creating zones of high and low pressure. So certain areas of the Earth are evaporating a lot of water. That water is getting into the atmosphere. That's lowering the density of that air. That air is rising. That's low pressure. Meanwhile, in other parts of the Earth, the air has lost that water vapor as it's reached higher and higher into the atmosphere, into the troposphere, and it cools and sinks with a higher density. These differences in air pressure cause pressure gradients. Pressure gradients. I don't know why all of these are number 1. That's some weird thing. I don't see why. But anyway, a pressure gradient. How the pressure changes over a given distance. Pressure gradient. Air moves across pressure gradients from areas of high pressure to areas of low pressure. And here we see what's called a map of surface streamlines, which is the wind blowing from here, an area of high, away from the high, and it always blows counterclockwise away from the high, and those lines end up arriving at a low where they circle around the low counterclockwise. So the streamline map is really interesting in that it shows us how air leaves the center of a high and heads towards the center of a low, from high pressure to low. And of course, these streamlines are winds that are blowing. And here you can see there must be a small low pressure in this area, and a small low pressure in this area, and some low here, because air is moving into those areas. Somewhere down here, there's some kind of a high, but it's not as well defined as this one. And here we can also see that the streamlines are very close together, indicating that the pressure is changing somewhat rapidly over the surface of the Earth. Now, this is a picture of how air rises and falls north and south, say, of the equator based on temperature. Actually, this is not north and south of the equator. This is actually going across the Pacific Ocean east to west, and this is actually showing you a convection cell that is famous in the equatorial region of the Pacific that is associated with a weather phenomenon called El Nino. But what we see here is in the western Pacific, air near the equator is rising, cooling, traveling laterally east-west, and then sinking as a high pressure over Central America and Ecuador, Western South America. And it creates a convection cell. But we also have convection cells that head north and south, and I'll go over those in a moment. So, air moves from areas of high pressure to areas of low pressure, and that is also a way of describing the wind. So how do we measure and name the winds? Wind is measured with an anemometer or anemometer, like that movie, anemometer. But it's an anemo, from the ancient Greek, anemos, wind, anemometer, anemometer, anemometer. Anemometers are placed at least 10 meters above the ground to measure wind speed and direction. Now, why 10 meters above the ground? Well, if you put your anemometer right on the ground, the wind is coming in contact with the surface of the Earth. That contact creates friction. That friction changes the wind speed. So, you always want to have your anemometer up above the ground high enough so that friction is not a factor in your measurement. Winds are named based upon the direction from which they are coming, not where they're going. the direction from which they are coming. Sometimes it's a name, sometimes it's a number of degrees. So, a south wind could also be a wind coming from 180 degrees. A north wind could be also a wind coming from 0 degrees. But generally, and these are the ancient Greek names for winds. Many people have heard of Zephyr. I don't know if you've heard of any of these others, but Zephyr is a famous west wind. I didn't know the southwest wind was Lips. And here's Apeliotes, the east wind. Beautiful, beautiful words. Here are all the winds, though, by degree and directional name. And you can see a compass rose, which is what this is called, is broken into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different wind directions. North, north-northeast, northeast, east-northeast. Now, what's the difference between north-northeast and east-northeast? Well, north-northeast is between northeast and north. East-northeast is between northeast and east, and so on around the rose. And you can see that we have increments here of, looks like about 0, and then our next wind looks like maybe at 22 degrees, 22.5 degrees. Then our next one is at 45 degrees. So this actually must be, is that right? Yeah, 22.5. And then so on, every 22.5 degrees around the rose. And here you can see north is 0, north-northeast, northeast at 45, southeast at 135, east, of course, at 90. I skipped it. South at 180, southwest at 225, west 270, and northwest at 315. West, northwest. Winds and the Coriolis effect. Now, if you remember, the Coriolis effect is the effect that causes fluids, liquids, and gases on the surface of the earth to be deflected from a straight path based upon the rotation of the earth. Because of the earth's rotation, winds are deflected from moving in a perfectly straight path. In the northern hemisphere, winds are deflected to the right. In the southern hemisphere, winds are deflected to the left. This is known as the Coriolis effect. As you recall, the Coriolis effect is considered proof of the Earth's rotation. Highs and lows. Winds blow clockwise around a high and counterclockwise around a low. So here we can see the wind coming out, bent to the right, and spinning around that high, as it were, clockwise. Then, from the point of view of the observer of the wind, and that would be you in the high watching the wind leave, here you're watching the wind come towards you, and instead of going here, it bends to the right, bends to the right, bends into the right from your point of view at the center of the low, and rotates overall counterclockwise while being deflected to the right. Diverge away from the high, converge towards the low. Diverge away, converge towards. Away from the high, towards the low. Away from the high, towards the low. Wind is blowing. Friction and the wind. Friction between the ground and surface wind slows them and reduces the Coriolis deflection. So where there's friction, particularly over areas of diverse topography, with relief, up and down, up and down, up and down, the wind will blow straighter. Maximum friction is over rough land, while maximum Coriolis is over smooth ocean. The jet stream. This is a very important part of our weather, where high altitude winds in the upper troposphere blow from west to east with little friction, and they have a seasonal component where in the summer the jet streams are up further north, and in the winter a little bit further south. There are two streams, a polar jet and a subtropical jet, and when the polar jet dips down, we can have what's called that polar vortex. When it dips down, or in the summer when it dips down, it brings cool, dry air to our part of the world. So, the polar jet stream in the United States forms a boundary between warm and cold air masses, moving them north and south. Polar vortex is a jet stream pushing south in the winter. And so you can see that when this jet stream here pushes north, warm, moist air is going to come into the mainland of the United States. When this jet stream pushes south, cold, dry air is going to come in. So these jet streams vary quite significantly. Now let's talk about the generally predictable winds that blow around the Earth, called global winds. These are winds that blow from areas of high pressure to areas of low pressure. This general pattern creates convection cells that shape winds globally. Here, air, it turns out, around the globe rises and sinks in predictable locations. And here you can see how dry sinking air hits the Earth and then blows away from the high. And here you can see that air that's blown away from the high approaching a low and beginning to rise as it's picked up moisture over the surface. All right, here is page 14 of your reference table. And we can see that there is a pattern that creates global winds. The global winds are named here in the middle as northeast winds, southwest winds, northeast winds, southeast winds, northwest winds, and a final set of southeast, all named based on the direction they're coming from, and all defined by the latitude of their source. So we have winds, southwest winds, that blow from 30 north across our latitude in the 40s towards 60. Meanwhile, there are polar winds that originate near the poles that blow in the northern hemisphere from the northeast towards 60 north. So it turns out that 30 north, which has winds blowing from it, must be an area of high pressure, dry high pressure. And this must be an area here of lower pressure because air's blowing towards it. Meanwhile, the equator is clearly an area of low pressure because you've got winds blowing from 30 north towards the equator and winds from 30 south blowing towards the equator. And if we look now on the side view, we see some convection cells, Ferrel cell. I forget the name of this one. We'll see it in a second. And what happens here is that you see these vertical arrows coming off the Earth from the equator are warm, moist air rising, then sinking at 30 north, and then wind blowing down from 30 north to the equator. These are global winds. We also have a convection cell of rising air at 60 north and 60 south. We have a convection cell of rising air from the equator and then sinking at 30 south. And if we look at this, we see air sinks at 90, air rises at 60, air sinks at 30, air rises at 0, the equator, air sinks at 30 south, air rises at 60 south, air sinks at 90 south. And what is the quality of the air at each one of those latitudes? From pole to pole, cold, dry air. Then at 60, warmer, moist air. Not warm, warmer. Cooler, dry air at 30 north. Cooler than the hot and humid air. So it's cooler in relation to the hot and humid air. Then again, that cooler, dry air in relation to the equatorial region. Then warmer, moist air, warmer in relation to the polar air, which is cold and dry. And these are, it's Ferrel. So the first cell from the equator is the Hadley cell. I had it backwards. So this is your first cell, air, convection cell, air rising, drawing water up into it, a lot of water getting lost. The air has now lost all its water and it sinks back down. And here we have that jet stream, which can move these cells up and down depending on time of year and other conditions that influence it. Then we have the Ferrel cell here, rising at 60, with that polar jet stream near its apex or top left, not quite the apex. And then we again, in both cases, air is sinking with both these cells at 30 north. And 30 north and 30 south tend to be very dry areas of the Earth. Then finally, the polar cell starting, rising at 60, sinking at the pole, and cold winds blowing south. Warmer winds blowing towards 60 north, cooler winds blowing towards the equator in relation to the equator, the relationship between 30 north and 60. This would be warmer for the people at 60. So the major global winds, northeast and southeast trade winds, they blow from either 30 north, northeast to southwest, or 30 degrees south, southeast to northwest, towards the equator. 0. Those are your trade winds. And they got named trade winds because they were very good at moving sailboats from Europe, southern Europe, Spain, across the Atlantic towards the New World. And then as more and more people sailed, they began to see the patterns of these winds, and they got called trade winds because trade was dependent upon the wind. Then you've got the prevailing westerlies. They blow from either 30 north, southwest to northeast, or 30 south, northwest to southeast. So there you go. From the west to the east, southwest to northeast in the northern hemisphere, northwest to southeast in the southern. And then finally the polar easterlies. They blow from either 30 north to the southwest or 90 south to the northeast, okay? And they're blowing towards 60 north or 60 south. Those are your global winds. And again, these are the patterns. And these winds are actually very important in determining the ocean currents. At 30 north and south, a subtropical high-pressure zone exists. These belts are also known as the Horse Latitudes, characterized by calm winds and little rain, location of many of Earth's deserts. At 0 degrees in the spring and fall, an equatorial low-pressure zone exists where winds are calm. This belt of low pressure around the globe is known as the doldrums, or the intertropical convergence zone. So they got the doldrums. That word came about when people were sailing and they would lose their wind and they'd just sit and wait for the wind to come. This ITCZ, the Intertropical Convergence Zone, migrates north to 23.5 degrees north in the northern hemisphere in June at the solstice, and then migrates to 23.5 degrees south in the southern hemisphere in December. And this is actually a big part of what drives what are called the monsoons of South Asia and Southeast Asia. And here again, we can see the relationship between these global winds and the ocean. Here are your winds blowing from 30 north, south, towards the equator, and then up these winds blowing across from 30 north towards 60. So you get these gyres based on global winds. The currents follow the winds. There are also these things called local winds, which have generate what are called land and sea breezes, where during the day the sand heats up really quickly because it has a low specific heat, creates a zone of low pressure, air rises off the surface, blows out over the ocean, drops back down, and a high wind blows off the cool ocean onto the land, and that keeps people cool. One of the reasons people like to go to the beach in the summer. And then at night, it's reversed. A warmer wind blows off the land towards the sea, an area of high pressure a cooler wind, because the sand has cooled down because of its low specific heat. So now the land is cooler than the ocean, and it goes from high to low. And you also get this in the mountains. In the daytime, you can get it warming in the valley. The air rises, so you get a warm breeze as you're climbing the mountain, and then cool air sinks down towards the valley. And then at night, you get air lifting up from the valley and sinking along the mountain wall, and you get a cool breeze down into the valley. So local winds. And that brings us to the subject of condensation, which is an important and independent subject on its own. But before we go there, I'd like to see if we could take a quick look at a website called Windy, because windy is kind of exciting. This is the wind conditions right now. And right now is April 20th at, according to this, it's 12 a.m. Yeah, I don't know what that means. Oh no, we're at local time. So we're at local time 2:45. And what we can see is that we have a center of low pressure here with air moving counterclockwise around that center of low. We have another center of low pressure here with air moving around it, being drawn into the low. And do we have any highs? Well, we don't have any really prominent highs. You can see one here with air moving away from the high. It's not spinning as dramatically because you can see the isobars are much further apart so that it's not a lot of wind. A little bit more dramatic here where the high pressure is causing air to move towards this low, and you can see it's kind of bending it's definitely bending to the right, and if it continued it would go around in this manner. Here must be a high pressure zone, and you can see air bending to the right around a zone of high pressure. Maybe if we zoom out we can see that zone. Yeah, there's the zone of high pressure. Let's zoom out a little bit more. That's as far as we can go. And you can see a zone of high, and they're giving you the pressure reading in inches of mercury, which is not actually considered to be the correct units that we would use, given that we're showing isobars. So I don't know if you can change that. I don't see a way to. But in any event, this is called windy.com, and you can take a look at it when you look at this video. And with that, I'm going to stop.